for coming to my talk, and thanks to Olga and Sid for the kind invitation to be here. It's my pleasure to be in Lausanne, and yeah, I hope you can all hear me. So I am assistant professor in mechanical engineering and adjunct professor in applied math, and actually my background was also in applied math at UW. I work on data-driven manufacturing applications, and I have extensive collaborations with Boeing and Idaho National Lab. And so one of the priorities of my work is safe and interpretable ML and AI for safety-critical applications, and particularly targeting towards engineering and manufacturing applications, where you need guarantees on safety, and you use physics-based machine learning, as introduced in the previous talk, to get guarantees on performance and also do uncertainty quantification. So the title of my talk is Sparse Variable Interactions and Uncertainty in Data-Driven Optimization, and I will talk about two data-driven optimization problems in this work. So safe and certifiable AI in engineering applications is often required to be trustworthy and therefore human interpretable, and make it easier for engineers to make design decisions, and also for regulatory agencies like the FAA and in nuclear applications to certify models. So you need guarantees on performance. These models that you use need to be generalizable to new settings under small variations in model parameters. This is basically a robustness requirement because it's basically saying that if you vary your model parameters by a small amount, your prediction doesn't diverge or blow up. And that's connected to getting guarantees on performance in various decision-making and control problems. One of the things I will talk about is learning ODEs from trajectory data. So as in the previous talk, ODEs and PDEs are kind of the language of these problems and help us characterize and model the behavior of these dynamic systems and very complex engineering processes. So first I will talk about sparse system identification. And sparsity actually encodes something about the model design space. So we want models to have a small number of active terms, or in other words, they are parsimonious in the design space. So I will talk about sparse system identification for the majority of this talk. And this sparsity in the optimization is connected to sparsity in resources in a lot of engineering settings, where you often have sparsity in sensor measurements, and also limited control energy and control inputs in controlling and monitoring these processes. I will talk about time permitting an application in nuclear digital twins. This is a collaboration with Idaho National Lab, where we want to optimize sensors in the design stage of this nuclear heating prototype vessel that is placed into a reactor and model in real time using a digital twin of the process, the current state of that entire system with all of its connected subsystems. The issue here is the very limited number of sensors you are allowed, and this tends to be very common in the aerospace manufacturing applications as well. So we want to infer the temperature field inside this prototype vessel, which can be multi-phase and very complex physics, from often very constrained sensor locations and sensor placements. So one of the direct applications of sparsity in your model design space is the optimization of sensor placement for inferring temperature and flow fields inside complex engineering processes. As was so nicely outlined in the previous talk, there are two perspectives on this. Either you let the learning method learn its own representation, which can often be extremely complex and parameterized by millions or billions of parameters in deep learning models. This is a challenge in engineering applications because at most, we often have maybe 50 to 200 samples in many of the applications I work with of the flow fields or the measurements. Or you can constrain to human interpretable representations, which is otherwise the guiding principle known as parsimony. And this motivates the idea of promoting sparsity in your model design space. And I'll talk about exactly what this means, but this principle is very beneficial for physics-informed machine learning and inherently promotes interpretability, generalizability, as well as makes it easier to perform uncertainty quantification. The argument, of course, is that parsimonious models are inherently interpretable and generalizable, and the discovered equations that I'm going to talk about hold even in new settings when parameters of these equations are changed. This is much harder to do in a black box model like a neural network. But of course, there are constraints you can, like physics-informed deep learning, that you can introduce into deep learning. So I will talk about a system identification technique, sparse identification of nonlinear dynamics, where you want to identify an ODE from trajectory data, usually with a small number of samples, on the order of hundreds of time steps. So on the left-hand side, you have the discretized time derivative of your state variables, which are indexed by L. And the ansatz is that they are, the left-hand side is a sparse linear combination of nonlinear library terms, which are user chosen and populate the library theta. So this is a schematic of the method. I hope you can see it. So on the left-hand side in this system, the Lorentz attractor are the numerical derivatives, x dot, y dot, and z dot. And on the right-hand side are polynomial terms of these state variables up to order 5. And these are given. And you want to solve for the sparsest model, or the most parsimonious model, by imposing sparsity of the coefficients, which translates to an L0 norm penalty, which is the number of non-zero coefficients that we solve for. There are different solvers for the sparse optimization problem, and trying to inspect and quantify their behavior is one of the goals of the work that we propose. And this method has been extremely successful, was introduced in 2016, and is readily deployed in seconds on a laptop. And you can simulate the identified system to forecast and to evaluate the goodness of it. There is an issue with this, as this is a chaotic system. So even if the correct model is identified, your forecasts can diverge. So we need a better way of quantifying the optimality of these solutions with respect to sparsity. So there are many variants of SINDI that have been proposed since then due to the success of this modeling approach. One of them discovers PDEs from snapshots of PDE data. And of course, this requires a lot more derivatives on the left-hand side. And as we know, taking numerical derivatives is very sensitive to noise. So there have been weak forms of SINDI that have been proposed that avoids taking these derivatives directly. And also ensemble methods that basically average the identified coefficients over an ensemble of trajectories to get a more robust prediction. And it has been combined with deep learning as well to discover a sparse model after training nonlinear embeddings of the input data. For example, if the states in your equations do not directly match the states from measurement or observational data. This can be useful for things like climate. And also, we directly investigate the sparsity structure imposed on the coefficient model, C. And this involves things like Laplace priors, which inherently promote sparsity, and also spike and slab models, which we'll work with. So all versions of SINDI solve some variant of this sparsity promoting least squares problem. So the first term is the least squares fit between the discretized library and the derivatives on the left-hand side. And the right term is a p-norm on the coefficient, on the library coefficient CL. And this is very well known to be sparsifying for p less than or equal to 1. In practice, we typically use p equals 1 because then you can use convex solvers. But often the motivating problem in sparse optimization problems in general is some optimization of the L0 norm, which is the number of model terms or design terms. And this is very well known to be non-convex, which is why this constraint is often relaxed to a norm between 0 and 1. And 1 when it's convex relaxation. So one of the questions we want to answer is, when is recovery of the differential equation possible in terms of the trajectory length, the sampling time step, and the noise levels? And oftentimes when you do sparse regression or any sort of convex solution for a sparse regression problem, there's the sparsity parameter lambda that needs to be tuned in order to balance the descriptive capability of the model on the left and also the sparsity of the identified coefficients. And this is joint work with my postdoc, Andrei Klishin, and our collaborators, Joe Bakarji and Nathan Kutz, who's also a co-author in the previous paper on parsimony and SINDI. So this is the mathematical foundation of this method. We're going to do sparse Bayesian inference. Again, this is not typically done in the previous variants of SINDI, except one of them. We use a prior that naturally results in the L0 optimization problem. The L0 norm optimization problem is an optimization over all possible coefficient sets in that library. So it is combinatorial in nature. But this prior of delta functions centered at the coefficients and a wide Gaussian prior naturally results in the optimization problem on the previous slide, where p is equal to 0. Remember that p is equal to 0 is often the motivating challenge behind all sparse optimization problems and is later relaxed to something more tractable or differentiable. We want to investigate the solution space of the L0 problem and try to identify the recoverability regimes of the model in terms of the number of data you have, your selection of the hyperparameter value, and an optimal value of these hyperparameters that results in true and correct identification, even for chaotic systems. We assume the typical Gaussian noise on the derivative, and we can use Bayes' rule to express the posterior of the coefficients, we can express this, we can expand and factorize this posterior over the power set of the coefficient sets gamma, and we get the sum of these likelihoods of the different coefficient sets scaled by a statistical weight, or z. So we use the tools of statistical mechanics to analyze this posterior distribution in detail and actually get explicit forms of the posterior distribution by evaluating all the coefficient sets for a small choice of n or for a small polynomial library. These statistical weights, or Z, is known as the partition function, similar to a Boltzmann distribution in statistical mechanics. And Z is the negative exponential of the statistical free energies. So we're going to evaluate the free energies of all the coefficient sets. This free energy for each coefficient set depends on these different terms that promote sparsity, and also depend on C and V. C are the covariance matrix of the library terms, and V is the cross-covariance matrix of the derivatives with the library terms. We can pre-compute all of these beforehand and sub-select 4 different coefficient sets to evaluate this rapidly. But still remember, we are evaluating all of the coefficient sets. This last parameter here is the size of the coefficient set times lambda. And this explicitly parametrizes the dependence of the optimal solution on the sparsity parameter, as well as the number of terms in that coefficient set. So, and this, the first term is termed scales as order the size of gamma log n, which is basically a natural sparsity promoting weight in the free energy, and it's related to Bayesian information criterion, which penalizes complexity of the models that are identified. So these can be related to classical information criteria in Bayesian optimization. So we actually evaluate this for the same Lorentz attractor that we identified before. And as you know, it's a chaotic system, and we want to be able to have an evaluation framework for optimality in the L0 sense, or in the true sparsity sense, without running the model forward in time, because this is a chaotic system with sensitive dependence on the initial conditions, even if the correct model is identified. So these are the trajectories for the 3 state variables. And shown on the top are the free energies, or the difference between the free energies of the different coefficient sets. The lowest on the y-axis is the difference of the free energies from the lowest free energy. And you can see that the lowest y-axis value corresponds to the optimal or the true correct solution. So for example, in x dot, you see the terms, model terms x and y correctly identified. For y dot, you see x, z, and y identified. And for z dot, you see x, y, and z identified, or z, as you might call it. Incidentally, we call this method z-Cindy because of the z in the partition function. But I guess here you would call it z-Cindy. And as you can see, the suboptimal solutions have a higher free energy and also a lower sparsity structure. And these correspond, as you might expect, to incorrect models. These bottom plots show the free energies as a function of varying n, or trajectory length. As on the previous slide, you noticed that the free energies were parameterized by n, which is the length of the trajectories. So we can actually notice transitions in the free energy with the size of your data. And we can further, we can see that they asymptotically go to a constant, and we can further stratify the free energies according to their sparsity levels by parameterizing according to that natural sparsity term, which is what you see in the bottom right. So this explicitly shows the dependence of the optimal solution identified with the size of your data, and when you cannot find the correct solution. So there are transitions of these free energy very akin to the kind you find like phase transitions in statistical mechanics. And another important aspect is that the probability of selecting a suboptimal coefficient set decays exponentially with trajectory length. And this is explicitly derived in the paper, which is up on arXiv. And you can see this exponential decay in the probability of identifying the suboptimal set, or P of gamma not equal to gamma star, for the 3 different state variables. We can also observe sharp transitions of the coefficient sets as we increase the sparsity penalty. If anyone's ever solved a sparse regression or sparse optimization problem scaled by a sparsity penalty, you know that it is challenging to choose the optimal value of the sparsity promoting penalty lambda. And here we can explicitly see that with the small amounts of sparsity penalty on the left, an incorrect model is identified at first with lower sparsity structure. And then as the sparsity structure parameter is increased, we identify the correct model corresponding to the lowest free energy on those fan plots. And you can see these sharp transitions in this phase diagram, essentially, of lambda and trajectory length space, which is a new way to kind of assess the quality or the solution space for these sparse regression problems. You can also write down the marginal posterior distributions for each coefficient, which is the inclusion probability of each term in the library, which is an interesting consequence of this approach. And you can actually do uncertainty quantification of that inclusion, of the inclusion of a certain term. And you can see that the probability of inclusion collapses or condenses to the mean value of that coefficient with the length of your trajectory. So we can basically identify the regime of correct identification of sparse regression problems. And it's limited, it's critically limited for in the case where you have too few terms, too small a trajectory, and you see this approximate, in the bottom right, you see this approximate critical noise level, which is proportional to the sparsity parameter to the 1/3. So this is kind of what we empirically observe, and it remains to be confirmed in the theory. What we have is basically a way of telling when is recovery possible using these sparse system identification techniques. And we can also get uncertainty quantification of the solution space. Or basically, we can, instead of doing ensemble sampling of different trajectories to get the bounds of the prediction in the forecasting model, you can look at the distributions of the terms that are included in the model. And you can calculate these explicitly for small polynomial libraries. So one of the consequences of this is we get an interpretable optimization landscape for system identification. And I don't have much time to talk about the sensor placement problem, but the sensor placement problem is also equivalent to a sparse optimization problem and has this combinatorial nature with the number of grid points and the number of sensors you're allowed. We apply the same procedure for optimal sensing for real-time monitoring of these nuclear digital twins. And we use a similar methodology to get the uncertainty quantification of reconstruction or temperature field reconstruction. I don't have the time to talk about this, but we basically take the sensor placement problem, we reframe it as this Bayesian estimation problem, and we look at the statistical energy landscape of 1 and 2 sensor interactions. Again, I don't have the time to go over this in detail, but it basically gives you an optimization landscape in terms of single point sensor energy, which is attracted to high variance locations in your data or the basis coefficients you're trying to learn, and sensor 2-point energy, which is repelled from highly correlated sensor locations. And you can use these to get basically an optimization landscape for sensor placement and resource allocation problems in general. And these are the results for that work applied to an extremely high dimensional example. And you can use 25 sensors to predict the entire temperature field distribution to within 2 degrees Celsius for this sea surface temperature data. And we use a very small number of sensors with the data driven prior to improve the reconstruction. And then we use this to the nuclear digital twin applications as well. I'll stop here, and hopefully you see the relevance of these techniques to engineering AI, which require guarantees and uncertainty quantification. And I'll take any questions.